Good afternoon, everybody. I'm Tom Kole from MACOM, and joining me is Ray Baker, and we're going to be discussing the reliability of our GaN on silicon product line. So we've had, next slide. So a little bit about MACOM's overall GaN strategy. So with the acquisition of Nitronics, which is now completed, MACOM is the only one that has both GaN on silicon carbide and GaN on silicon. And so it puts us in a very unique position to be able to drive the cost of GaN down and expand the applications and the different markets that can take advantage of what GaN has to offer. And so one of the things I wanted to mention in terms of our roadmap before we get to the reliability piece is that we have signed an agreement for 8-inch GaN on silicon wafers, so you can look for that coming from MACOM next year, 8-inch GaN on silicon, which will dramatically change the price landscape for GaN products. Next slide. So a little bit about the process that we're talking about. So this is the requisite SEM image of one of our GaN on silicon devices. And so you're going to look at it and say, well, gee, it looks like most other FETs that I've seen over time. And the answer is yes, that is exactly right. While GaN on silicon is very unique, it's not that different in terms of a GaN device. Most of the magic that makes GaN happens here, and we are now taking advantage by growing it epitaxially on silicon. We get GaN performance at a silicon cost structure. So that's what allows us to really move the price point down for MACOM's GaN on silicon. Next slide.
Okay, and you're going to see this theme throughout the slides here, and that is something that you already know. Temperature is the enemy of semiconductor reliability. So if we can keep the channel cool, if we can keep the transistor cool, the lifetime is going to be much better. That's just axiomatic. It's something that applies to just about every semiconductor process, probably every semiconductor process. So one of the myths out there is that silicon carbide is a much better thermal conductor than silicon. And in fact, that is correct. So if you go in the tables of properties of elements or compounds and you look at that number, yeah, sure enough, silicon carbide's better. But there's a lot more to the story. So what I'd like to do is kind of take you through a couple of examples and show you why that's not necessarily the tail that wags the dog. So if we look at, for example, thin substrates, and typical substrate thicknesses in the GaN world, whether with silicon or silicon carbide, are 2 to 6 mils. So these are fairly thin substrates to begin with. And using silicon, we can thin that down to 2 mils. It's not a difficult process. Lots of places can do it. It's very repeatable, very low-cost thing to do. So we can thin our silicon substrates to improve the thermal conductivity. So if we look, for example, at silicon carbide at 6 mils versus silicon at 2 mils, 2 mil silicon is actually better. So the substrate thickness has a lot to do with the overall thermal performance. Next one. So here's another example from two products that we make. This is kind of a Generation 1 product. It's the NPT 25100. It's about a 100-watt FET in a standard metal ceramic flange. This is the NPT 1010, which is also a 100-watt device in the same looking ceramic flange package. And if you look at the numbers here, here's all the various components that make up the thermal resistance of that entire stack up. And if you look at that, first of all, you'll notice that from Gen 1 to Gen 2, we went from 1.8 C per watt down to 1.4 degrees C per watt. How did we do that? We thinned the substrate. That's one thing we did. And the other change that we made is that we improved the thermal conductivity of the ceramic flange. We went from a copper tungsten to an almost pure copper flange. So those two things together greatly reduced, and these are the kind of things that we're doing in our latest generation, both 28 and 48 volt parts, to get the thermal conductivity, reduce the thermal conductivity. And if you look at this number on a 100-watt part, 1.4 C per watt, that's a very good number. That's comparable to the best silicon carbide parts that you'll see out on the market today. So here's an image of those two transistors under the QFI, thermal scope. And we actually look at these things under operation and we can look at the temperature of the channel. And here is an apples to apples comparison of the junction temperatures on those two devices. Here's the Gen 1 part, here's the Gen 2 part. And as you can see, a lot more heat in that Gen 1 part. Again, we just made two simple changes: thin the substrate, improve the package. And if we look at some of our latest parts, this NPT 2022, you're going to see some more about that in some later slides, but that's a 100 watt 48 volt device. It's in a plastic package, so we're already handicapped. But if you look at the numbers here, the theta JC is 1.3 C per watt, and you compare that to other 100 watt devices that are out on the market today in silicon carbide, in ceramic packages, and you can see that 1.3 watt number, C per watt, stands up very well against all the best competitor parts out on the market today. So I want to really dispel the belief that silicon cannot be a compelling substrate for GaN products. It absolutely can be. You have to do a couple things different.
So we'll talk a little bit about what we do in terms of process reliability and how we qualify the GaN on silicon products, and more to the point, how we prove that they are reliable. And so in terms of our first step, it's really the process qualification methodology that we use. So we actually go ahead and characterize the end-of-life mechanism, and we do that by employing a temperature-accelerated life test. And the whole purpose of this is to gauge and use temperature as a way to accelerate and through the Arrhenius equation, predict what the lifetimes are going to be for this process under normal use conditions. And so for that, we do a 3-temperature accelerated life test that's very commonly done in the gallium arsenide industry and other 3-5 semiconductors. And we do that with a setup of step stress tests to determine the right temperatures and the right times that we target to run this test. And so when we do that, we actually run 3 different temperatures. We use the Arrhenius equation, we extrapolate back, and that's what gives us the median time to failure for the GaN on silicon process. And so the question then is, well, when do we do this? Well, we do this when we characterize a new process, and we do it if there's any significant changes to the process over time to continue to prove that the process is reliable. Next slide. So this is what the results look like. So this is our half-micron GaN on silicon hemp, and this is done on a 3-temperature life test basis. So we've run at each of those 3 temperatures from 305 down to about 265 C. And so when we do that, and it's also very important to note that all of those fall on the same line. And so when you look at this type of data and this type of analysis, it's only meaningful if you have one slope, because that's indicative of the failure mechanism that you're talking about for the process. So as you can see, they all fall on a very nice regressed line. And so when we extrapolate back at about a junction of 200 degrees C, is right at our million-hour MTTF target. And that's what we like for our products, 1 million hours, median time to failure at a 200 degrees C channel temperature. Okay, and there is one point I want to make on how we characterize the parts. So we showed you some thermal images for the products using a 3-micron spot size infoscope 2. We use the same method for our life test parts characterization as we do our products. And why that's important, to you as the end customer, it's because you can look at our junction temperature and infer directly the reliability off of this plot to gauge, what your median time to failure is and the lambda that you would use in your system level reliability calculations. Okay, next.
Okay, so that established our 28 volt process reliability. And the next thing, a couple years ago, we wanted to embark on a 48 volt product line. So one of the first things you worry about, okay, when I move to 48 volts, what do I need to do different? What do I need to worry about? Well, the most obvious thing is probably breakdown voltage. A 28 volt part, you typically see breakdown voltages about in the 100 volt range. But when you go to 48 volts, because of Viswar and various effects in typical amplifier circuits, we need a 3 to 4x margin. So at the 48 volt node, we need to prove that these things will hold off 200 volts of drain voltage without failure. So this is kind of typical curves. We'll run the device up into a high voltage and see what the leakages, see how the leakages change. So we embarked on a simple experiment. One of the most obvious things is the drain to source spacing. So we did some experiments to see what those need to be to make a reliable 48 volt product. We had a little bit of experience in it because here's our generation 128 volt device breakdown, and as you can see, it's rolling up about there at about 140 volts. We had an effort underway to really improve the ruggedness of our 28 volt devices, probably starting about 3 or 4 years ago. And we found that if we increase the drain to source spacing a little bit, we could improve that breakdown voltage, which of course improved the Viswar tolerance, especially at high temperatures. So this GD3 node here are some improvements we rolled out to the 28 volt product line, 28 volt product line about 3 or 4 years ago. So if you extend that even further, we had a pretty good basis to guess what we needed to do for 48 volts. And as you can see, now you're seeing breakdowns in excess of 200 volts. That's what you need for 48 volt products. Okay.
So as Ray said, when we scaled up the device, now the question is, okay, did we create a different failure mechanism? And so by being very conservative in the way we laid the device out and scaled the drain to source spacing, we were able to go ahead and repeat testing on a large sample of parts, several different life test groups that we ran. And as you can see, they fall pretty nicely on that Arrhenius plot single mechanism line. And so lo and behold, if you remember what I had mentioned in our previous 28 volt process, we were right about 200 C for 1,000,000 hours MTTF. And so lo and behold, we go look, we do the test, we crank the numbers, and lo and behold, 200 C again for an MTTF of 1,000,000 hours. And what that's indicative of is, yes, indeed, we were conservative in how we laid out the device. We did not create a new end-of-life mechanism. So given that, you'd expect to see a very similar failure distribution and median time to failure for the 48 as with the 28, given they're the same mechanism. Okay, next one. Okay, so now we'll get into the product side. So our product reliability now, so if you could think about the process, right, and now I'm going to take that engine, the die, the GaN hemp die, and I'm going to take the GaN on silicon die, I'm going to drop it into a chassis. And the question is, what happens now when I take the very good reliability of the process and I put it in a package? How are we going to prove that that's reliable? So to give you our methodology, we sit down with a very large group of people. We brainstorm a similar table to like what you see here. We look at all the potential ways that that part can fail in the package. Examples like die cracking. Now you've got a die inside a package. It's subject to the stresses of assembly and cycling at a customer site and all the things that can cause it to, as I say, fall off the Arrhenius plot and impact the reliability. So what we do is go through a pretty exhaustive list. We design a stress plan to go ahead and qualify a test group for each of these stresses, and we do that to prove that the parts are not, that they are robust against and do not have any of these potential failure mechanisms. Okay. So when do we do that? So typically, anytime there is a change, things, failure modes can occur from process changes, different processing steps. So we look at all of that, and then we go ahead and do that if we change a part. So initial product qualification when we release it, then we would do it if there's anything changed about the process. We change assembly houses for the package, we change package materials. It goes back through this process and we requalify it to make sure that there's been no detrimental impact to the reliability that we've demonstrated previously. And so this is certainly not an all-encompassing, but a representative list of some of the types of stress testing that we've put our GaN and silicon through. And so you can see various things like shake, bake, rattle, and roll. We characterize for temperature cycling. For some of the cavity packages, we do mechanical shock and vibe. For some of our new plastic packages, we do all sorts of air-to-air temperature cycling. A variety of things, again, with the proof being that if we can get through and prove test by test and stress by stress that we have none of these potential mechanisms in, that's how we demonstrate our reliability. So a little bit about the high temp operating life test, which is something that when we talk to customers, they always ask about. And so these are accumulated over several years for both our 28 and 48 volt processes. So this was a redo when we moved our foundry several years ago. We verified again through several hundreds of parts that, you know, in accumulating almost 3.5 million equivalent device hours, again, we're statistically showing the reliability of the product. And so with our 48 volt process, we went a little more aggressive, and we've actually performed at 225 degrees C channel temperatures. And as we accumulate that, we've really spent the lion's share of our capacity on qualifying that new 48 volt product line and accumulated quite a large number of equivalent device hours in the process.
So here's an example of our newest 48 volt part, again in the plastic package. And one key point here is that it's important to test the process at the extremes, because the thermal resistance of the substrate changes with temperature. And in fact, whether it's silicon or silicon carbide, it gets worse with temperature. So it's one thing to measure that at 25 C or a nominal junction temperature. What you really want to know is what is it when it's hot, because unfortunately that's where you're going to be operating in the power amp world most of the time. So we actually measure this thermal impedance at 225 C. Again, we're actually above where we recommend that you operate it, but we want to make sure that we really bound that well, really give you a worst case number that you can use in your reliability analysis. Yes. And we also want to know that that part is capable of CW. That's kind of one of our claims to fame in our product line, that many of our devices will actually operate CW. So we test the same way. This isn't a pulse test. This is absolutely put it on the chuck, get the chuck hot, bring the part up to temperature by biasing it, and really see what that junction does when all of that is operating as you would in a CW application. So we take that information from the Arrhenius plots, and here's the takeaway for you, or one of them. That is, stay down in this green box, right? This is the box where as long as you're in this area, you're guaranteed to have 1 million hours of reliable operation on average. Again, just make sure you keep that junction temperature where it belongs. And that's in the data sheet. It's a well-seen number. And again, it just ties back to all of the thermal analysis and the reliability studies.
So I often get the question as we're out talking with customers, well, what exactly does a life test setup look like for some of your products? And so given that a picture is worth more than 1,000 of my words, I brought some images here that show one of our test sets. So we have 6 of these in the company, and they're continually running and accumulating more equivalent device hours for the products. But this is a 32 position, and we use this for anything 25 watt and below. And this allows us to come in, bias a part up. There's a hot plate. We can elevate the temperature up to get our target junction temperature of 200 or 225 C. And we can drop RF connectors on there, quick connect, and actually do measurements in situ during the products actually running. So we can characterize pre-post and determine pass-fail. And so that's one of the systems we use. And now if you look at some of our larger 100 watt and 50 watt devices, these are 6 foot tall burn-in racks. They can operate, there's up to 200 watts per position, and there's a total of 100 positions per rack, and we have 4 of these racks in the company. So it really allows us to continually test and verify the process reliability of the GaN on silicon. And you'll find that these things are almost in continuous use, running product 1,000-hour, 2,000-hour operating life tests, again, aimed at statistically showing through lots and lots of parts and over time and over wafer lot to wafer lot that the GaN on silicon process is reliable.
So one of the other things customers like to do to power amplifiers is operate them into poor loads. And of course, this puts special stresses on the part. And again, going with the theme of temperature, when you operate a power amplifier into a poor load, the junction temperature can really skyrocket. So one of the things we learned working with customers in the jammer market in particular is that they needed simultaneously full power, saturated power, high base plate temperature, and high Viswar. And you have to be able to withstand that at all phase angles. So we went through an extensive characterization, and this was when we really made some improvements to our 28-volt process to be able to serve this market and to withstand this. And the nice thing is we learned some things that have rolled into our entire product families. So all of our new products have this kind of ruggedness built into them. So we roll this over all Viswar, over all phase angles, up to 10 to 1, 15 to 1, in some cases 20 to 1, to really see what the parts do when they're in stress.
So a little bit in terms of where GaN on silicon has been used. A question I often get is, well, GaN is relatively new, but how long and how much and how harshly has it had to survive? And so one of the things I want to just share with you, we're about a month away from hitting the 1 million device shipped milestone for GaN on silicon. And we've demonstrated excellent field reliability, virtually no returns in that time. And we're designed in and have been shipping production in volume for nearly 6 years on a military radio program. Extremely harsh conditions, humidity, all sorts of cycled on and off, storage conditions, all the potential failure modes that we talked about previously. And we participated in that and survived very well and very reliably across time. So just a little bit of a benchmark that we can share in terms of where some of our volume GaN on silicon customers have used our parts.
Okay, so we've gone to great efforts to make a good process and great efforts to make a good product, and then we hand it to you. This is where things often go wrong. So what I'd like to do is try and, just based on my experience and kind of watching customers over the years, here's a few of the things to pay attention to when you actually drop these into your product. Things to make things go right. So one of the simplest ones is a good bias circuit. And there's lots of ways to mess this up. It's surprisingly simple. Bias on a GaN device has to be sequenced. Absolutely, positively have to do that. It's a depletion mode device. If you put 0 volts on the gate and you turn on the drain, the part will destroy itself almost immediately. You'll have great thermal load. It draws lots of current, lots of power. See ya. So make sure that your bias circuit is well designed. And there's kind of a second layer to that. You may do everything right and find out that your power supply guy does something unexpected, or he puts some kind of glitch that causes the gate supply to momentarily to dip or to rise. So I have seen customer problems where there have been transients on the bias lines, or RFI or EMI that somehow gets into these little charge pumps that are typically used to generate the gate voltage. So this really deserves some attention in your designs. A good precaution, especially in the higher power devices, is to put some kind of monitor on the gate current. Gate current is an excellent way to see what the transistor's feeling, if you will. If the gate current starts to grow, normally, under nominal conditions, there's very little or no gate current in these devices. But as you overdrive them, typically 3 to 6 dB of overdrive, you'll start to see that gate current rise. And you'll also see it rise under Viswar conditions. So that's another good thing to watch as part of your overall housekeeping on your amplifier. If you've got some kind of gate current increase or you see the gate current rising, it's probably something wrong. Time to back off the drive, do something to protect the circuit. And finally, Bison decoupling. Lots of ways to mess this up, and it's actually an underappreciated art because there's a lot of challenges in this Bison decoupling stuff. You've got to worry about the video bandwidth of your modulation. You have to worry about low frequency stability. You have to worry about decoupling into other parts of the circuit. So this really deserves some care and design. And another interesting thing that comes up on GaN circuits in particular, they're often used in wideband applications. Octave bandwidth, decade bandwidth. And when you do that, that little inductor that you put in the drain supply may be resonant, or it may be resonant at a harmonic of your operating frequency. And when that happens, you'll see dips in the gain, you'll see efficiency problems. So the wideband challenges only make this more difficult. Stability is actually pretty easy to achieve in these devices. If you notice on our reference designs and reference designs from other GaN suppliers, you will typically see a resistor in the gate supply. That resistor does a couple things, but one of the most important things is it adds low frequency stability. So that resistor value is generally important. And if you think about this circuit and you go down to DC, this is essentially the equivalent circuit that you have. Perfect. This is what guarantees your low frequency stability. And finally, one other problem that frequently occurs, especially as we've rolled out surface mount products over the years, you have to consider the effect of the circuit board. And I'm seeing that in more application notes from various manufacturers. In fact, in some cases, the circuit board contribution can be 50% or more of the actual device. So you think you've got a device that has 10 degrees C per watt performance, you put it on a board and it may be 15 degrees C performance because of the thermal impedance going through the circuit board. So you've got to make sure that you follow the recommended footprint that's typically in the data sheet. Use lots of vias, use a thin board if possible, use lots of metal, and I'll show you another example here. On the TO272, we've rolled out some parts in that package, in the high power package. There's a special thing you have to be careful here. If you simply do what you do with a normal ceramic package, you put 2 screws in it, it's not going to work, because the package will tend to bow in the center and not make contact with the heatsink. So there's actually a special little clamping device that holds and puts pressure on that package and keeps that flange in good contact with the base metal. Viswar stands on its own. It should watch Viswar, especially in the larger, higher power amplifiers. We want to add protection for that. And just generally know what the operating conditions are. Know what power dissipation is, either through status and monitoring. Again, Viswar protection. Just pay attention under all conditions, overdrive, underdrive, Viswar, and so forth, temperature, voltage, to make sure that you stay within the thermal limits that you think you are. Here's an example of good surface mount practice. This is a little eval board that we make for the MPA 1003. And again, if you just simply throw this circuit board on top of the heatsink, what kind of thermal path do you have actually under the device? So what we do is we recommend that you add 2 screws near the device, as near as possible, to make sure that circuit board is actually in full contact with the heatsink below. And you may want to add some thermal epoxy there or something just to make sure that you have absolute metal contact, metal to metal, all the way down to the heatsink under the device. And finally, I want to show this. This is actually a Viswar graph of one of our devices under very, very high Viswar sweep. And I mentioned to you why you want to monitor gate current. Well, look what happens at certain phase angles as we go through a high Viswar. We see the gate current come way up. And there's lots of things happening on this graph. Dissipation's going all over the place. The junction temperature is going to get very high. But the gate current is telling you, the part is telling you, I am very overdriven right now. I'm really overdriven into this very, very bad load. So again, it's a good message to remind us why gate current's a good thing to watch in your designs. And you can use that actually to, again, help protect the circuit and maybe provide some ALC or some feedback that says, hey, back off. I'm in a bad place right now. So. Oh, want to do that? Okay. Alrighty, let me do kind of one last thing here. So here's our NPT 2022, and these calculations are actually very simple. You can almost do them on the back of an envelope, and here's an example. So we've got a 30 to 512 broadband amplifier using our 2022 100-watt 48-volt device. In a typical case, you might want to put out about 100 watts. And we know in our reference design, we see about 60% efficiency. So you can go through the numbers, and that's about 68 watts dissipated DC. We're putting a little bit of drive power into it. That's got to go somewhere, right? So that's the total dissipation into the device. Here's our thermal impedance. And we're assuming a few things here, aren't we? We assume that it's 1.3 degrees C per watt, which is the device alone. So if I have a heat sink under this that is not well connected to ambient or doesn't have a good thermal path to the environment, I might need to add something to that number. So this is a little bit ideal, but let's assume it's mounted on copper and so forth. That's probably okay. So we come up with a 95 whoops, did I touch that? 95 degrees C per watt, or 95 degrees C junction temperature rise, and of course that's going to be on top of our 85 degree max base plate temperature. Then we end up at 180 degree junction temperature, which is very, very good. We know from that Arrhenius curve at 180 C, you're at 1,000,000 hours plus times 10 plus times 10, so you're probably at 10 million or 100 million hours of operating life under that junction temperature, and that's CW conditions all day long. And again, that would make a very, very reliable reference design. So that's a real-life example, and it shows how easy these calculations are. But you've got to pay attention to just a few details here. Okay.
Okay, thanks everyone.